All right, let's get started. So you got your exam on Friday, and we'll do the. Okay, ready to start? Here we go. Let's start. Okay, let's get started now. Ready? Here we go. So we got the exam on Friday. We'll do the same thing as normal. Try to show up about 9:30. We'll try to get it going about 9:35, and we'll let you have till 10:35. To study, you go to exam prep and homework solutions. Over here on the left. There you see it, exam 3, April 7th, sequences and series. So here's some suggestions for studying, also some practice problems from the book. If you have the online, if you're using the online text and you're having difficulty finding these problems, just shoot me an email. I will try to update this and give you more specific section information if you're using the online text. And then here's just a bullet point of skills and concepts. Let's see. Got to make sure that Maclaurin and Taylor series is on there. So if that's not in this list, it definitely is on the exam. So stuff we did Monday and today is on the exam. I will update this bullet point list today to reflect that. Okay. Any questions on the exam? Oh, and so then for homework, so that second set that was due today, I extended that and gave you 3 more tries. So the one that was number 27, there were 3 problems. So I made that continue. That's still open until Friday at 9 a.m. And you have 3 more tries. And then there's 1 more set based on today's stuff. And that's also due 9 a.m. It is number 28 will also be due 9 a.m. Friday. Again, both those sets, stuff for the exam. So just think about that homework as part of your studying for the exam. Any questions? Yes, sir. This one, okay, yes, thank you for asking. This one, you can use a basic scientific calculator, but you can't use a graphing calculator. So you could, if you have one, they're like $8. You could borrow one from a friend, or you could buy one. They're like $8, or many of you probably have one. But no graphing calculators for this test. They do too much. Okay, they do too much. So any basic scientific $5 to $10 calculator, okay, is allowed. Other questions? Okay, so we're talking about Taylor and Maclaurin series. Let's go ahead and let's build a Maclaurin series for cosine, just cosine x, plain old cosine x. Okay? Cosine. We're going to build a Maclaurin series for cosine. Here we go. So this is our basic form for the Maclaurin series that we saw last time. The nth derivative, so f raised, that nth power is talking about the derivative. The nth derivative evaluated at 0, and then over n factorial times x to the n. So really, if we're building one of these, so there's kind of two things to these Maclaurin and Taylor series. There's building them from scratch, like we're about to do. We're going to build it from the ground up. And then there's using ones that we know to quickly generate variations of functions, which we'll also talk about. But so in this case, here we're going to do this. We're going to generate the Maclaurin series for cosine from scratch. Okay? And what does that mean? That means we need these. We need the nth derivatives of what? Cosine. So in this case, f is cosine. Our function is cosine. So we need the nth derivatives of cosine evaluated at 0. And once we have those, then we can just write this down. Everything else we just plug those in and we write this down. Okay, so what I recommend is we make a table for that. And so we know that n starts at n starts at 0, and then we're going to let it equal 1, 2, 3. This is how a series works, right? N starting at 0 to infinity means n takes on all the integers. Okay?
And so then the nth derivative, in this case, f of x is cosine x, right? We want f of x to be cosine x. So the 0th derivative is just the function. It's just the function. Okay? So what is the function evaluated at 0? What's cosine of 0? 1, right? Cosine is the x coordinate on the unit circle. Angle 0 means pointing on the positive x-axis. X coordinate is 1. Okay, so now we take the first derivative of cosine. It's the first derivative of cosine. Negative sine x. Okay? Evaluated at 0. 0. Okay? Second derivative is going to be the derivative of that. Negative cosine of x. Evaluated at 0. Negative 1. Okay? Derivative of negative cosine. Positive sine. Evaluated at 0. Derivative of sine. Cosine. Evaluated at 0. Okay, so this is just gonna keep repeating, right? So now that we're to n equals 4, we're gonna see the same pattern repeat. So negative sine x, evaluated at 0 is 0. Derivative of negative sine, negative cosine, gives us negative 1. One more, sine x, gives 0. Actually, let's just do one more, 8. Derivative of sine is cosine, evaluated at 0 is 1. Okay, so now let's practice just writing out what this means. So without looking at your notes from last time. So just generically, this right here, not related to cosine, but just this summation right here. You see that? Think what, right? See that? Think what? Apart from cosine, right? Just the generic Maclaurin series would be what? I got my list today. Okay, you're next on the list. Do you have a nickname? What do you go by? Zoe? Okay, you're up. Okay? F at 0. Right? Uh-huh. Good. Yep. How's she doing so far? Good. We'll do one more. Actually, I want one more, and I'll do that one up here. Fourth derivative evaluated at 0 over 4 factorial times x to the 4th. And on and on and on. Is that what you wrote? So this is the Maclaurin series, just the generic form of the Maclaurin series, right? Now written out the long way. That's a 0, no, that's 6. Okay, so now what we're going to do is we're going to plug in those derivatives evaluated at 0. And what's going to happen? Every time n is odd, what's going to happen to our term? It's going to go away, right? So every time we have an odd value of n, those are going to go away. We're only going to actually end up preserving the even values of n. N equals 0, 2, 4, 6, etc. Okay? So here we go. So f evaluated at 0 was, so 1 plus 0x, right? Plus, so second derivative evaluated at 0 was our negative 1 right here. X squared over 2 factorial. Plus, third derivative was 0, so 0x cubed. All right, plus, this is the fourth, yeah, so 1 is the coefficient, so our fourth derivative evaluated at 0 is positive 1, this would be 1. What will be the next non-zero term? Do we have, oh, we've got that, right? So next non-zero term will be negative 1, x to the 6th, and the next one will be positive 1, x to the 8 over 8 factorial. Okay, so now we want to go back and we don't want to have all these zeros in here, okay? What we'd really like is a new form of this. So we'll say k. So let's have a new, we're going to call a new index k. And for this first term, we want k to be 0. And now instead of this being, the index being 2, we want this to be 1. We don't want to have these skipped terms, right? So we want to rewrite cosine as a summation, but we don't want to have a 0 term every other index, every other value of the index, right? So we'll call a new index k, and we want, when k equals 0, we want to get 1. And when k equals 1, we want to get this term. And when k equals 2, we want to get this term. And when k equals 3, we want to get the, etc. Does it make sense? So now I want to rewrite this as a sum so that I'm not zeroing out every other term. I want to just get the non-zero terms. So I need a new formula, right? I need a new formula based on k. It's going to be the sum now as k goes from 0 to infinity. And so I have to look at my value of k in relation to the term that I have. So when I have k equals 1, I get negative x squared over 2 factorial. When k is 2, I get x to the 4th over 4 factorial, etc. When k is 3, I get negative x to the 6 over 6 factorial. See if you can write the formula in terms of k now. What formula in terms of k will generate these non-zero terms the way I've indexed with k? Okay, Jaiwei, you're up. Tell me. What's that? I'm looking for the formula now in terms of k that's going to generate these terms. Where's Gabe Kaplan? Yeah, did you get it?
Yeah.
Tell me.
So it's
Negative 1 to the k plus 1
times
x to the 2k.
all over 2k factorial.
This is what he's proposing. Agree? Close?
Close.
So let's see. So if we plug 0 in, then we get what? -1 to the first. So I like this, right? But when I plug 0 in, I want to get +1. So how do you want to change that? Yeah, just okay. How about now? Okay, yeah. So now this, the nice thing about this is every value of k gives us a non-zero term now. But it generates the exact same sum that we had when we just followed the Maclaurin series. Okay? So this is our Maclaurin series for cosine x. And we know that it generates these terms. Okay? How do we find the interval of convergence? So I want to know, so for what values of x is this series, is this, this polynomial a valid representation of cosine of x, right? So it only may be in some interval that it works, right? Or it may be all real numbers. How do we find out? Ratio test, right? So if we do the ratio test on this, so what we're gonna, you've had plenty of practice. If you want to do that later, you can do that. If we do the ratio test on this, we're gonna find that no matter what x is, the limit in that ratio test is 0. Therefore, radius is, the interval is all real numbers, and the radius is infinite. Meaning that the more, so now this is centered at 0, right? So we know at first, for just a few terms of the partial sum, it's going to be accurate close to 0, and then as you add more and more terms of your partial sum, it's going to converge it's going to converge to cosine x, kind of starting from the middle, moving its way out. So we saw that last time with e to the x. Okay, so because it's centered at 0, we get really good approximations of cosine x with just the first few terms, and then we need more and more and more terms to get a good approximation for cosine x farther away from 0. And the farther away you get from 0, the more terms you're going to need for that series to converge on cosine x. Okay, so questions on that so far? So a really important thing, this whole section, sequences and series, is numerical analysis. How do machines calculate values of like irrational numbers? How do machines calculate values of irrational or infinite decimal numbers? How do they do it? Do they have a data bank that stores every value of cosine x? No, it would take too much memory, right? There'd be an infinite number of values you'd need. So there's not some database of values in your calculator in any software. So what does it do? It uses power series, or like for instance this Maclaurin series. So let's take a look at that. So here I have cosine of 8/9. Okay, cosine of 8/9 is 0.630275, etc. That's an irrational number. Those decimal places will go on forever and non-repeat, okay, and will not repeat. So they'll be decimal places forever. So how did my software here, graphing calculator, it's called, how did it come up with this decimal value, 0.630275, blah, blah, blah? Okay, well, it's going to be some kind of approximating process like the Maclaurin series that we just found. So if I want cosine of 8/9 and I want to get an approximation for that using my Maclaurin series that we just find, how am I going to do that? How am I going to get cosine of 8/9? What do I do? Yeah, plug in 8/9 for x. And so then I'm plugging it into this polynomial. So I can use a partial sum, which is a finite polynomial, to get an approximation. So let's start with, what's the first partial sum of cosine x? What's the first partial sum? 1, right? 1, that's the first partial sum. All right? And what's the second? And so that, not a very good approximation. What's the second partial sum? Okay, But what is the second partial sum? Is it negative x squared over 2 factorial? 1 minus, right? So now I'm going to do minus. Not what I wanted to do. I want this. 8/9. So 1 minus 8/9, what? Squared divided by 2 factorial. And look what I get. It's already correct to the 10th place, right? So the second partial sum is already correct. It's 0.60 instead of 0.63. All right, so then the calculator says, no, I need to be better than that, right? I don't want to tell my user that it's 0.604. That's not close enough. I want it to be correct to whatever, 8 or 10 decimal places. So third partial sum is what? The second partial sum, then plus one more term, right? So plus 8/9 to the 4th divided by 4 factorial. For this particular, so for cosine of 8/9, just the third partial sum is like, it's correct to the 100th place, even almost the 1000th place, right? So even just the third partial sum of this is pretty close. And if you want it closer, so now we're going to do minus, what, to the 6th, divided by 6 factorial. So look at how close this is already. The fourth partial sum is correct to how many decimal places? 4 or 5 even, right? 4 decimal places is correct to the 4th decimal place. So as you keep, so what about the sequence? Tell me about the sequence. What has to be true about this sequence? The sequence has to converge to 0, right? For a series to converge, the sequence has to converge to 0. So these terms are getting really, really, really small. They're getting smaller and smaller. So by adding and subtracting these smaller and smaller values, we're talking about smaller and smaller fractions that we're changing this sum by, right? We're changing the sum by smaller and smaller fractions. Okay, so here's the deal. Time out. So we're taking attendance, but we still have a lot of people using cell phones, even when we're asking you not to. You're just using your cell phones in class. So if we catch you using your cell phone, you're absent today. That's it, the rest of the semester. So Ben and LP know this, and if they see you using your cell phone, absent. Okay? Thanks. All right. So with each term, we know it's getting smaller and smaller, approaching 0. We're tinkering with our sum by a smaller and smaller amount. So we're keep fine-tuning it to more and more decimal places. That's what's happening as you keep adding terms of the sum. We'll do one more. See how good this is. All right, so this is like correct to what? 6 places. So it wouldn't take very many more. So the software is going to keep adding terms until it determines that many decimal places is correct, and it's going to stop, and it's going to give you that answer. It's going to say, this is what cosine of 8/9 is. But we know, okay, that's only correct to 8 or 10 decimal places. So your technology, your computers and calculators are using these kinds of processes to generate approximations for infinite decimal numbers. Okay? Doesn't make sense. Okay, so another thing about these is we can use, so polynomials are like the friendliest kinds of functions we have. They're really easy to differentiate, they're really easy to integrate, and so if we can, say we wanted to know about the function, so g of x, say we want to know about x cosine radical x. So that's kind of a complicated function. If we wanted to integrate it, that we don't have a technique for that. right? So it might not even have a closed form antiderivative, okay? Meaning an easy formula whose derivative is that. Okay? So and if suppose we want just a version of that function that's easier to work with, right? Well, we can use the Maclaurin series for cosine x then to do that, right? So if cosine x is this power series, or this polynomial, then what would x cosine radical x be? What would x cosine radical x? Well, we can write x cosine radical x very quickly now as a power series. Instead of generating that from scratch, that'd be ugly, right? Because we're finding derivatives, and so we'd have power rule, and then the power rule would just blow up by the second or third derivative. We'd have really complicated derivatives as we're doing second, third, fourth derivatives. So rather than building it up from scratch like we just did for cosine, we can use what we found for cosine to find a series for this pretty quickly. All right, so how would we do that? If cosine x is this, what's cosine radical x? What's cosine radical x? She wants to replace all the x's with square root of x. Does it work? Yeah, right? So cosine x is a function, right? It's a function operating on x. And this is telling us whatever your value is of the independent variable, replace it where x is. Okay? Well, now we're saying the inputs or the independent variable is radical x. So it would be 1, right? 1 minus x, or 2 factorial, plus x squared. So the square root, so what will the power be? Cube, right? Because this is power 1/2. 1/2 of 6 is 3. Thank you. I was just checking. Okay, plus it'd be x to the 4th over a factorial, etc. And so it took a little bit of work to generate cosine x, right? But now having cosine x, we just wrote down the power series for cosine radical x in like 30 seconds. This is 6. Okay, but we wanted x times cosine x. So what's the power series for x cosine radical x? Everyone do it, go. What's the power series for x times cosine radical x? Okay, Sophia, hello. You're up. Are you here? Can you tell me? So I've got cosine radical x, and now I want the power series for x times cosine radical x. So what are we doing to cosine radical x? What are we doing? We're just multiplying by x, right? So what would you get if you took the power series and multiplied it by x? X, right? Minus x squared over, right? Keep going. You got it. That's it. Very good. And on and on and on. Got my water. So again, like I said, there's kind of two aspects to building these Taylor and Maclaurin series. There's building them from scratch, like we did e to the x last time, we did cosine x today. And then there's, once you have a basic power series, you can very quickly generate variations on that. Okay, what's that gentleman's name right there in the gray shirt? He's yours. Yeah. Unless that's a calculator. Is it a calculator? Okay. All right. Okay, so x cosine radical x then is this. And we just wrote that down in less than 30 seconds, right? Okay, so then, again, why do we want this? Because polynomials are really very convenient to work with, and we know if we get enough terms of them, we get a really good approximation. Okay? So for instance, now we could do, so x, the integral or the antiderivative of x cosine radical x, it probably doesn't have a closed form, a nice formula as its antiderivative. And even if it does, it'd be very difficult to figure out. Our techniques would fall way short. So instead, what if we just wanted a good approximation for the antiderivative of x cosine radical x? We just want to get something close. What could we do? Yes, sir? Right. Yeah, so do the antiderivative of the power series instead, right? So instead of trying to chisel at this with our techniques, let's do the antiderivative of this. And as long as we get enough terms, then that antiderivative can be really close to the actual antiderivative of that. Okay? So, who's next? Where's Michael Walker? Michael Walker here? So can you do it? So let's get an approximation for the antiderivative of x cosine radical x. X squared over 2, good. Good. Is it minus? Yeah, minus x to the 5th. Etc. See what he did? So we're just doing the antiderivative now, which is easy for a polynomial. So this is a big advantage to these power series. Polynomials are easy to work with. They're easy to work with. And with a Maclaurin and Taylor series, we can write any function as a polynomial, or with an infinite number of terms. And then if we wanted, we could work backwards and get a formula for summation, right? So we could do, so if we said, start it with n equals 2, like this, what would it be? Anybody do this fast? So -1 to the k, -1 to the n. That looks right. Okay, then x to the n over, it's like n, well, 2, 3, so this looks like n, and then times what factorial? So when n is 3, we get 2. When n is 4, we get 4. When n is 5, we get 6. That's a little tricky. So 3 gives us 2. 4 gives us 4. 5 gives us 6. I think it's -2 times 2. Right? You're going to subtract 2 from n and multiply by 2. So subtract 2, get 1 times 2 is 2. Subtract 2 times 2. So it will be, we're going to subtract 2 and multiply by 2, and that's the factorial we need. Which is the same as 2n minus 4. Okay, so that's the power series for the antiderivative of x cosine radical x. Okay, any questions on this? Yes, please. What else did you want to do? Like, so you could shift the index, first of all. Yeah, if you start n equals 0, so you're moving back your index by 2, so all these n's would have to be increased by 2. This would stay the same, then you'd have x to the n plus 2, and then you have n plus 2, and then you'd have, what, 2n factorial? Yeah, so that's just shifting the index, yeah. You shift the index, and remember, however you shift the index, all your n's are going to make it the same series, all your n's are going to change in the opposite direction. Other questions? Okay, so let's, so we haven't really done any Taylor series, so we'll do a Taylor series example and see that. So what is a Taylor series? Taylor series then can be centered around any value, not just 0. Not just 0. So let's do, here's a good one. Taylor series for natural log of 2x about x equals 3. So the a value, this means a equals 3. Okay, so that's our Taylor series centered at 3. Now it's going to be the nth derivative evaluated at 3, and instead of x to the n, it's going to be x minus 3 to the n. So this will center, it will center things around 3, and I'll show you the picture when we're done. Okay, so we're going to, our approximations will converge starting at 3 and working its way out from 3. Picture, you'll have to see the picture to really see that. All right, so here we go. So we're going to look at starting at 0, values of n, derivatives. So the nth derivative of the function is just the function. Okay? ln, so evaluated at 3. What's ln 2x evaluated at 3? ln of 6. First derivative. Remember derivative of natural log? 1 over 2x times 2, which turns out to be x to the negative 1. So you get 1 over 2x, then times 2, so the 2's go away, and we got x to the minus 1, evaluated at 3. 1/3. Okay. Derivative, second derivative is the derivative of the first derivative. Derivative is negative 1 times x to the negative 2. Which is, in order for us to generate the formula, I'm not going to simplify. I'm going to do this. I'm going to do negative 1 divided by 2 squared. 3 squared, right? I'm going to leave it like that, though. I'm going to leave it like that. Okay? Third derivative. It's going to be negative 2 times negative 1 times x to the negative 3. So I really need this to be moved over. I need room. Okay, so what we have negative 2 times negative 1 times 3 to the negative 3, or over 3 cubed. Fourth derivative. Can we just do it all at once here? So I'll just go right to plugging in 3. So it'd be what? The derivative is going to be negative 3 times negative 2 times negative 1 times x to the, or 3 to the negative 4. So I think we got enough to see what the formula is going to be. So when n equals 4, we got negative 3 times negative 2 times negative 1 times 3 to the negative 4. I'm just holding on to all the negatives. So I'm always going to multiply, it's always going to be a negative. So this one will become positive, so this will be negative 1, 3 to the negative 1, and then this will be positive, and then that will be negative, because it's 3 negatives, and the next one will be positive. Who asked me that? Is that good? Okay. So I'm just holding on to all the negatives here, but you're right. It's gonna go positive, negative, depending on if it's an odd number of negatives or an even. Okay, so I think we're ready to write this down. Here we go. When n equals 0, we're going to have our natural log of 6 over 0 factorial times this thing to the 0. So that's just all 1. So the first term is going to be natural log of 6. Then we're going to have plus 1/3 that's over 1 times x minus 3 to the first. Stop me if I lose you. Now n equals 2. So we're going to have what? Negative 1/9 2 factorial. I put it up here, is that okay? X minus 3 squared to save room. So my negative 1/9, that was the second derivative evaluated at 3. There's my 2 factorial, x minus 3 squared. Plus, now it's going to be positive, what, 1/27 over, it's going to be x minus 3 cubed over 27 3 factorial. Yes, thank you. Right. Yeah, positive 2 over 27 is our nth derivative taken at 3. And then we have the 3 factorial, and then x minus 3 cubed. All right, then minus. So what is happening here? This 2 was really 2 times 1. This is 3 times 2 times 1. This is really factorial, right? What factorial is that? So we have 3 factorial over 3 to the 4th x minus 3 to the 4th. We do one more term. It's going to be, one more term will be 4 factorial over 3 to the 5th, x minus 3 to the 5th. Okay. Do you follow that? So what is, the only thing we really had to do here was, I'll circle in blue, was these derivatives. The derivative evaluated at 3. Everything else, I'm just following the formula. 3 factorial, 4 factorial, and then x minus 3 to the 3rd, x minus 3 to the 4th. So this, what I'm circling in blue, was was actually the actual work we did over in the table. Everything else, I'm just writing down. I'm just writing down according to this, the n factorial and the x minus 3 to the n. Does it make sense? Yes, please.
For your last two, wouldn't you need a 4 factorial and 5 factorial? So it matches the form? Because you had the 3
So when n equals 5, I'll have 4 factorial and 3.
Yeah, on the bottom. Because it's over n factorial.
Oh, I just forgot the factorial. This here, right here? Oh, and I missed it here too.
Yeah.
Thank you. So there's a 4 factorial there and a 5 factorial there. Right. Very good. Okay. So let's get the formula for this. So notice that the natural log of 6, this first term, it's different than all of these. So it's just going to hang out by itself. We need it. It's part of it, but it's not going to be part of the pattern, right? It's not part of the pattern. So we're going to write natural log of 6 plus, and now we're going to start our general form summation. So maybe we start with n equals 1, okay? Maybe we start with n equals 1. And this is for 1, 2, 3, 4. This is the fifth right here. So here's the fifth. This is for n equals 5 right here. So this is how the formula is easy to see. So what factorial do we have if this is n equals 5? N minus 1 factorial. X minus 3 to the n over 3 to the n times n factorial. Now notice, look what we have. N minus 1 factorial on the top, n factorial on the bottom. What does that result in? Just an n in the bottom, right? So n factorial is n factorial n times n minus 1 factorial. So we could just make this whole thing, we could just, here, I'll do red. Just take away that, and take away that. And just have n in the denominator. So quick, let's see the picture. So this is the power series for the Taylor series for natural log of 2x centered at x equals 3. Questions before I take this away? Okay, so here we go. Here's natural log of 2x. Here's the first partial sum. So is this consistent with what we got? Essentially. So it's a little bit different form, but natural log of 6 plus this is what we got, just a little bit different here. But it's the same sum. Okay? Here's the first partial sum. Here's the second partial sum. So ln of 6 plus x minus 3 over 3. Notice it's really accurate where? Centered at 3. It's really accurate centered right here at 3. With each additional term that I add, I get more accuracy away from 3. But it's the derivatives, more and more derivatives are correct at 3, working away from 3. All right, so the blue one is the right one, the red one is the, so notice what's happening in terms of interval of convergence. Is the interval of convergence all positive numbers? Watch it again. So here I'm going to add more terms. Keep adding more and more terms. What's always happening? It diverges after 6. Do you see that? So if we were to use the ratio test on this, we would not get
an infinite radius.
We're actually going to get a radius of 3. So here's our center, a equals 3. See, this is a good practice problem. Do the ratio test, and you'll find that the interval of convergence is from 0 to 6. And so we're seeing that as I add more and more terms. After 6, it doesn't matter how many terms I add. It just the power series diverges after 6. So the interval is from 0 to 6 with a radius of 3. And that's a good practice problem. Do the ratio test, find the interval of convergence on that, confirm that it's 0 to 6, radius of 3.